Waalaikumsalam, Doctor.
Good. Okay.
Waalaikumsalam, Doctor.
Good. Thank you very much for responding. Thank you very much. Okay. I already shared right now. Currently, I'm sharing the QR code, but somehow it's nobody managed to scan, isn't it? Let me see whether I got something wrong here. Okay. Something wrong here. Something is wrong here. No. Let's scan. Let's get our QR code first. 2 p.m. Okay. Oh, you guys already scanned. What happened just now? Yeah, so for those who just joined, oh, he already left. He scanned and he left. Okay. Yeah, right now there's the how many of you? 23. The number of scan is 21. Participant 23. Wow. Okay. We start. Give some time for those who haven't scanned. Once I guess nobody is coming. Only 21 of you guys. Okay.
Doctor,
Yes.
I couldn't scan, doctor. Can you show the QR code like properly?
How can I show it? I'm sharing it already. What do you mean showing it? I'm already sharing it now. Sorry?
I think the top of it is like it's a bit
Oh, I see. Okay. You mean it's crop up at the top. Thank you.
okay, thank you.
Okay, there's 25 of you guys currently, and there's 25 scan. I guess nobody's coming anymore. Okay, if there's if anybody's coming, we will just show it later on. Let me see what are we going to do today. So let's unshare this. Oh, Ibrahim, you just dropped by. I mean, you just joined us. Okay, 1 more minute in order to just complete it to 5 minutes past 2. Okay, about your test tomorrow. On Tuesday, on Wednesday. Okay, I've seen the questions. Frankly speaking, if you are very well, if you know the stuff, you can make it on time. If you don't know the stuff, you will not be able to complete it. That's what I have to say. It's very long. It's not difficult. It's just long. That's it. So you have to really know the stuff. Then you can get it done faster, quickly, or else you might not make it. And there's 3 questions. 2 of it will be on a single reaction, and the other one will be a double reaction. And you really need to know your stuff. Okay, it's 5:02, so I'm going to stop sharing this QR code, and we will look at our lecture. We are still in chapter 8. Okay, we're still looking at solution and mixing. Is this your last week of the semester, or is it going to be next week, guys? Are you guys you will have your final week, I think, somewhere in February, the first week, 7th of February, I think it start. Your final will start.
I think,
So
Doctor, next week is last week.
next week is the last week. Thank you. I thought so too, because we still need one more week to cover chapter 9, that is heat of solution. Okay, so today we still have to cover chapter 8, finish chapter 8. Chapter 8 will, chapter 9, what we're going to cover next week will be a continuation of chapter 8, which is mixing and solution. And there will be one question on that on chapter 9, but you need to know chapter 8 before you can do chapter 9. So let's try to finish chapter 8 by today, hopefully, inshallah, and we will look at chapter 9 by next week. Okay, so we yesterday we were looking at how to get the enthalpy for heat of mixing, heat of solution. You are given table B11 in the appendix, or you can also use any enthalpy chart. For example, you have sulfuric acid, sodium hydroxide, any of it is available, you can use it. So today we're going to look at adiabatic mixing. When you have adiabatic mixing, that means your Q is equal to 0. Even though it is stated that it's adiabatic mixing, you have to write the full equation first. You have to write your open system or your closed system equation and drop the terms that need to be dropped, give reasons why it is being dropped, and then you end up with Q equals to 0. Okay, so whenever you have adiabatic mixing, the good thing about it is that if you have a graph, you start with this is your H1, the enthalpy of the first input, and this is the enthalpy of the second input. So if you have the two values available, so for example, this is H1, and then you have this is H2, if you draw a straight line, you will have your third enthalpy, which is that of your output, somewhere on that line. It will be automatically on that line. You can find it as long as you know the composition of your output composition. If you know that composition, you should be able to locate or get the value of your enthalpy of the output. So this only occur when you have an adiabatic mixing. Yeah. So let's look at one example. Adiabatic mixing. Let's see. Okay. This is an example that's not inside from your textbook. You have 2 pounds of water, liquid, at a temperature of 100 degrees Fahrenheit. We are using English unit or American system because the chart is in English unit, so we're going to use English unit, or else we might have to do conversion. So that's a bit messy, so stick with what we have. So you have 2 pound mass of water coming in at 100 degrees Fahrenheit. Yeah, I don't have the statement, I'm just give you the block diagram. And you have 1 pound of sulfuric acid solution also coming in 100 degrees Fahrenheit. That's 1 pound. You will have an output solution. That's the composition is not given. You just give it a nomenclature of X for the composition of sulfuric acid, and the mass flow rate, the mass flow is M. So you're supposed to find the outlet temperature of your output. What's the temperature? Yeah, so you can do the meter balance to solve for the mass coming out, or the the M, the value of M, and the value of X, the composition of sulfuric acid. You can do that using meter balance. But in order to get the temperature, you need to have this graph where you have the isotherm, which is the temperature. So first, you need to find the value of X first. Once you know what is the value of X, you can locate it in this graph, and then you join the enthalpy of H1. If you join the enthalpy of H1 with that of the enthalpy of H2, if you wanted to find enthalpy of H3, then you should be able to get the enthalpy of H3. But if you in this case, enthalpy of H3 is not the unknown. The unknown is temperature. So you just need to join the 2 points, the 2 points of the inlets, and you will get a straight line. Once you get that straight line, knowing the value of X, you should be able to find the temperature of T. Let's do this problem. Let's try to solve for M and X first. Your basis, you need to write down your basis. So you have 2 inlets. Just use one of the value. So let's say 2 pound mass of water. Right. That is your basis. So that's liquid water. Just okay, write down that. Now do the meter balance. I'm going to do the meter balance over here. Total balance. You have 2 pound plus 1 pound, okay, equals to M. So obviously M is going to be 3 pound. And your balance on sulfuric acid balance, you're going to have no sulfuric acid in the input for water, but you have 0.6 times by 1 sulfuric acid in the second input is equals to X times by M. Your M just now you managed to get it and it happened to be 3. So that means your X, if you do the calculation, 0.6 divided by 3, that's going to be 0.2. So that is your pound mass per pound mass of your composition output composition M. So if you locate that in this graph, let me use a different color. Your composition is 0.2, so that will be the straight line going through. Oh, I'm not getting a straight line here. Undo that. 0.2 is 20%. So on this graph, that's on the 20% vertical line. Why I'm not getting a straight line? I really need to get a straight line. Hold on. Okay, that's good. Okay. We don't know the temperature of the output. We do know the composition. Now, the first input is pure water. Your first input is pure water. So if it's pure water, you know that this scale, your x-axis is percent weight of hydrogen sulfate. So pure water will be on the y-axis on the left. So pure water will be somewhere on the y-axis here, but it's there. It's on the y-axis, but it's on the left. So based on the temperature of the input, the temperature of that water is coming in at 100. So you should be able to know where is the location of that pure water. So this is 100. This is 100. Yeah, that's 100. So if you just go along that curve or isotherm, so this is going to be the first location of your input for pure water. Okay? So that should be enthalpy H1 if you need that value. Alright, so the second input, you have 0.6. The composition of hydrogen sulfate is 0.6 and the temperature is 100. So you should be able to locate that point on the graph, 0.6 mass fraction and 100%. So that will be 60. If I draw a straight line again, that's 60. Yeah, and 100% is this line. So that's your second point. Yeah, so now you have 2 points. You need to join it in order to get the temperature of your output. So I'm going to draw a straight line from this is going to be, if you project this somewhere there, that will be your H2. Okay. So now let's join your H1 and your that 2 points. Make sure it's straight. I'm trying to get a straight line and I'm not getting it. Okay, that is my straight line. Okay, and the point of intersection of the vertical line through 20% and your straight line is here, and that is the location of your output, the solution coming out of the mixer. So if you want to find H3, then if you just project it to the horizontally to the y-axis, that will be your H3. Yeah, if you need to find H3. And now let's look at the question asked for the temperature. So the temperature, I'm going to use it's a blue line. This is the isotherm that passes through that intersection. And that's the curve that passes through that intersection, and it happened to be 120. So that is your temperature of your output, the temperature of the final product, which is the required temperature that we need to find, 120 degrees Fahrenheit. So that's the final temperature. So if you want to find the enthalpy, for example, H1, you should be able to read it off the graph. We read it off the graph. That is about 68, roughly 68. So just rough estimate, that's about 68 BTU per pound mass. And if I want to find the enthalpy of H2, I just have to look at the scale. That's about 30 minus 110. That's 110. This is minus 110. So I'll write that as minus 110 BTU per pound mass. And if I want to find the third enthalpy, all I have to do is just read off from this graph. Okay, I think it's about 10. This is 0. That's 0. That's 20. So it's 10. So your enthalpy 3 is equal to 10 BTU per pound mass. So if the question further asks for what is the amount of, Q is already 0. So it shouldn't be asking for Q. So I don't know. In this case, the question didn't ask for any energy balance. It's just asking for the final temperature. So if you need any energy balance, then you will be the enthalpies are already there. Okay. So, but Q is already 0, so you don't need to find for Q anymore. But this is how you solve the temperature of your output. If you want to find the temperature of your output, you join the 2 points of the 2 inputs. And if you know the composition of your output, then you should be able to get the temperature as you can see how we just did it. Any questions? Guys, any questions? You just need to join the 2 points. Pure water is always on the y-axis, the left side, not on the right side. The 100% on the right side is for pure sulfuric acid. So pure water is on the left-hand side. So if you know the temperature, you should be able to locate the first location. And if you know the composition of your second input and the temperature, you should be able to get the location of your second input. So if you join the 2 points and get a straight line, where it intersects with the composition of your output is where your temperature is going to be located. Okay, guys, any questions on this? Any questions? Nobody going to ask anything? But this is a very straightforward example. You have 2 streams coming in and 1 stream getting out, and the mixing is adiabatic. So let's look at one example from your textbook. It's about the same thing. It's about the same. The question is about adiabatic mixing. Okay, so this is adiabatic mixing. You have pure water at 60 degrees Fahrenheit. You're going to mix 100 gram with that pure water is not 100 gram. That pure water is 250 gram. Okay? You're going to mix it with 100 gram of aqueous sulfuric acid, composition 80%. Also at the same temperature of 60 degrees Fahrenheit. Since it is adiabatic, the question asks what is the final temperature of your final solution. What's the temperature? So let's just draw our block diagram. Yeah, if we draw a block diagram, yeah, this is going to be your input. There's another input coming in. Another input, and you're going to have another output. Okay. So your first input is going to be water, 250 grams of water. Going to mix it, it is at 60 Fahrenheit. We're going to mix it with 100 grams of solution of 0.8 wet percent gram per gram of sulfuric acid, and the rest is water. So you're going to end up with the temperature again is also 60. Excuse me. Your final solution, let's just say it as m gram of sulfuric solution. The composition we don't know. That we're going to be gram per gram sulfuric acid. 1 minus x gram per gram excuse me, of water. Okay, the temperature is the unknown. You need to find that temperature. Okay, you need to solve for the material balance first, because you need to find the composition of your solution. So do the material balance, the total balance. This is very similar to what we have just done. 250 gram plus 100 gram is equals to m, and that's going to be 350 gram. Okay? So your composition on sulfuric acid balance. For the first input, you don't have any sulfuric acid because it is just pure water. So there's no sulfuric acid. But for the second input, you do have 0.8 mass fraction of sulfuric acid. So if you need to multiply it with the flow rate in order to get the actual amount of sulfuric acid. So 100 times by composition, the mass fraction is equals to x, the unknown, times by the total amount of solution, 350. So you should be able to get your x. And if you do the calculation, at t divided by 350, you will get 0.229, roughly 0.23. Why we round it off? Because you're not going to use right until to the third decimal places in order to locate it on the graph. So now we're going to locate the composition of the final solution, 0.23, but this graph is based on wet fraction, so it's going to be 23. So I'm going to use a red color ink. So 23, this is 25, so 23 will be somewhere there, roughly, just an estimate. Okay, I'm going to draw a straight line. Okay. That is going to be my straight line. I don't know how far I need to go, whether it's still, but I don't think it's going to reach 100 and 200. And so now, your first input is at 60 pure water. So just like I mentioned just now, pure water is on the y-axis. Pure water is on the y-axis on the left side. So that's pure water. And this is pure water. Oops. That is pure water. Okay, so y-axis, so you have the temperature 60, and this is 60. That is 60, the isotherm for 60. So if you just move along that isotherm, so this is going to be your first input, the location of your first input. And if you want to write down, that will be your enthalpy 1, if you're going to write it as enthalpy 1. Okay, so let's change that marker first. I need to write it to see. If I want to get enthalpy 1, if I want. Yeah, but I don't think I'm going to need it, but just write it there. So next, the second input is 80% sulfuric acid, again at the same temperature of 60. 80%, so I should be able to locate it on the graph. On the same isotherm, 60 degrees Fahrenheit, and it is at 80. So this is my 80% vertical line. So it intersect here So that is going to be my second point. So if I want to find the enthalpy, I just need to move horizontally. I should be able to get 100 and minus 120, the enthalpy of the second input. So now, just like what we did just in the previous example, we joined the 2 points using a straight line. Right? Okay, that's a straight line. Where the point of intersection is, that is the point of intersection, is where the final solution is going to be. Okay, so if you look at that, it's slightly more than 120. Let's see, 100, more than 100. This is 100. This is 100. You move along that line, it doesn't really fall on that intersection. Slightly more. Slightly more. So depends if the textbook, the answer, if I'm not mistaken, the answer for this example, the textbook give it a temperature of approximately 100. But I think this is more than 100 based on my diagram. I would give it to be maybe 110, something like that. Just estimate. It's just, this is 100 degrees C, and the one here is 120. So it will be maybe 110, maybe 110 roughly. So I'm going to just give it a temperature of 110. So that is going to be 110. But the textbook, the answer in your textbook is 100. So that's, every time you use a graph by visual inspection, you're not going to get the same answer like everybody else. Depends on how accurate you draw the line and how you kind of estimate the temperature. So everybody going to get a different value, but then the difference will be not that big in such a way that it will be, it's definitely not right if it's too big. Okay, so any question on that? That's the first part of this question. The answer given here is 100. We get 110. So it's okay. Because we are using the graph to get the answer. We don't do direct calculation. Calculation, definitely everybody should be able to get the same answer. But if you're using graph, by visual inspection, there's no way, not everybody is going to get the same. Okay, so that's the first part. The second part, what is the maximum temperature that you can achieve and how much water need to be added? How much water need to be added in order to achieve that final temperature? So now, for the second part, you're not going to have this amount of water. You need to find that amount of water. You don't know that amount of water. So we're going to give it a symbol. Let's say this is going to be M1. That's going to be M2. I don't need the dot here because there's no mass. It's not red. Okay? So now you need to find the maximum temperature that you can achieve. The maximum temperature that you can achieve will be on this straight line. On the straight line here, it will be on that straight line that we just draw. Let me undo that. Okay, it should be on this straight line. Okay, but where is it? You just need to find the tangent. If you have a look at the isotherm, they are all curving. Okay, so let me use a red color. So they are all curving. Definitely, it cannot be less than. It cannot be any less than 140. It cannot be 140 because 140 is below that straight line already. Okay, it could be 150, 160, but 160 is not touching that line. That line is touching the isotherm somewhere in between 140 and 160. If you look at this curve, the tangent is going to be somewhere here. Okay, let me do that using a different marker. Different color. Let's use dark green. Okay, so if I draw this line, following the trend of the isotherm, it will touches that straight line that we just drew somewhere here, somewhere, let's see, somewhere, the tangent will be somewhere here. Okay, That's the tangent. So this 100 that curve is a 150 degrees Fahrenheit curve roughly, because it's midway between 140 and 160. So that's 150. So the maximum temperature that can be achieved will be tangent to your straight line. And it so happen in this case that temperature is 150. So I'm going to write that temperature over here. The maximum temperature for part B, 150 degrees Fahrenheit. Once I manage to get that 150, I'm going to change this to 150. Okay. I need to find the composition X, the composition of X by looking at the where it intersects. The 150 curve, where it intersects the straight line, I should be able to find my composition somewhere down here. Okay, so let me undo that in order to get a straight line. This is just approximate. Okay, so what is that composition? It will be about 58% sulfuric acid, roughly. Yeah, so that is where it intersects tangent, where the straight line meets the 150 curve. So that is about 58%. So we're going to write X is equals to 0.58 and gram per gram of sulfuric acid. That is your composition of the final product. So now you know what's the composition already. You can find the material balance. You need to find the value of M1 and M2. The question asks for what's the amount of water that you need to add to the mixer. So in order to do that, you need to do the material balance. So now we're going to do the material balance. The input M1 plus your 100 gram of your solution is equal to M2. M2 you don't know. Now you do this is the total balance. This is the second part of the problem. Now you do the sulfuric acid balance. Your water has no sulfuric acid, so there's no M1. So 100. The input of the second solution is still 0.8. The composition is 0.8. It's still the same. So you have your composition just now that you get for X 0.58. So you can multiply that with M2, which is your final amount of the solution. You already managed to get X here, 0.58. So you should be able to calculate M2. So because the only unknown is M2, so M2, if you do the calculation at T divided by 58, that's going to be, is it correct guys? Sorry, 0. It should be at T time divided by 0.58. Okay, that's 137.93 gram. What is the solution in the textbook? This is just M2. Okay, that's M2. So now, putting that value here, 137.93, you should be able to solve for M1. M1 is equals to 137.93 minus 100. If you do the if you rearrange it, you bring over this 100 to the other side, so it should be minus. So you end up with 37.93 grams. So that is your final amount of water that you need to add up. That you need to add to the mixer. The answer in the textbook, if we look at the answer over here, we get the same temperature, and the answer is 38 gram. We got 37.93 gram. That's about 38. Okay, so that's how you get the amount of water that you need to add to the mixer in order to get the maximum temperature of 150 degrees Fahrenheit. Any questions? How to get the maximum temperature? It must be tangent. Your temperature must be tangent to your straight line that join the 2 points. So your straight line, you already managed to get it from part A. So you just need to find where that straight line touches tangentially to one of the curve of the isotherm. So it so happened that it is not directly touching 160. So it's between 140 and 160. So you know it's just a rough estimate of 150 degrees Fahrenheit. Any questions? Anybody? Any questions? Sometimes this type of question, you need to find the material balance and the energy balance together, because sometimes you don't, somehow if you know Q is equals to 0, you should be able to use the energy balance to solve for any unknowns. So sometimes you need to solve both of it, the energy balance and the material balance simultaneously. Any question, guys? Is it very clear? No questions? Okay, good. Nobody's asking anything, so I'm assuming that everybody is clear on this. Okay, so let's then continue with what we're going to cover. Okay, we are done with adiabatic mixing. This is one example. We have done this at 5.3 is also adiabatic mixing. Now we've been looking at enthalpy concentration diagram. In fact, we have already done enthalpy concentration diagram. We have looked at one example, which is for sulfuric acid, the one that we did just now. This is enthalpy. That is enthalpy, the y-axis, versus the concentration. So that is enthalpy concentration diagram. It's the same thing. Okay, except that in this, you'll be looking at a different type of enthalpy concentration diagram, whereby you have the tie line. The tie line is actually the temperature line. This is the temperature line. Just now you have the temperature isotherm is curved. Here it is a straight line connecting the saturated vapor and the saturated liquid. That means anywhere in between these two lines, anywhere between here, you will have a mixture of vapor plus liquid. Okay, if it's on the bottom line, here, if it's on this bottom line, then it will be 100% liquid. As it progressed upwards, that liquid started to change, in some of it started to become vapor. Some of the liquid started to become vapor, and by the time it reached this top line, everything is completely vapor. Everything is completely vaporized. So it is the saturated vapor line. Here, everything is saturated vapor. Okay? So in between the two lines, saturated vapor and saturated liquid line, you have a mixture of vapor and liquid. And the tie line, which is that broken line, the tie line is the temperature whereby both the vapor and the liquid are in equilibrium. The vapor and the liquid, that is the mixture, is in equilibrium at that temperature, at that tie line. So this is, you're going to encounter this in separation 1 when you do separation, when you do distillation, and when you do absorption. But this is one example of another concentration, enthalpy concentration diagram. Over here is your enthalpy. Okay? And here is your concentration in mass fraction. And this is your tie line. The tie line is the one connecting the two, the saturated liquid and the saturated vapor curve. In this case, it's curving. It's not really a straight line. It's the upper and the lower lines is not really a line. It's curving. Okay, please take note of the reference state. Every time if you are using this graph, your reference state must be the same as that written for the graph. You cannot choose any other reference state because that is your source of data. So you are restricted to the same reference state. Okay, now this is in degrees Fahrenheit. The isotherm is in degrees Fahrenheit. There's another. This is the lever rule. We're not going to really use much of it. The lever rule. Over here you have point B. This is A. This is C. Okay? On the same ice tie line, on the same temperature. So this is liquid. At the bottom is liquid. Here is vapor. So if you want to know the value of the vapor, the ratio of vapor to that of ratio of liquid. This is L, liquid, amount of liquid, and V is the amount of vapor. If you want to know that ratio, you get the distance from A to C. You measure that distance, okay, and then you measure this distance, and then you divide the two. You should be able to get the ratio of the amount of liquid to that of vapor. Most of the time we don't do that. We just use the enthalpy to do that. Okay? But if you want to do it, it's also possible if you just get that amount minus by this amount and then get this amount. You just deduct the get the difference from the mass fraction. Okay, so you should be able to get the distance. You can also do that. Okay, now let's see this example. 854. Yeah. Everybody is very quiet today, very tired, most probably, or sleeping. It's already 2:42. This is the time, the most time when everybody is sleepy. Let's have a look at this example. Let's read through the statement, problem statement. You have an aqueous ammonia solution in equilibrium. That means your vapor and your liquid is going to be in equilibrium. In a closed system, okay, you have a closed system at 160 and 1 atm. Okay, so that is your solution. The liquid account for 95% of the total mass of the system. The question asks you to use this graph to determine the weight percent of ammonia in each phase and the enthalpy of the system per unit mass of the system. Okay, the answer over here is I have the answer written here. So you have 1 mass of the system. So you have 1 pound mass of your ammonia aqueous. The question already mentioned per unit mass. Per unit mass, so you're going to use 1 pound. Okay. So out of that 1 pound, 95% of it is going to be liquid. So 0.95 pound is going to be liquid, and the rest is going to be vapor. It's going to be vapor based on the statement 95%. Okay, here is said the liquid phase is 95%. Liquid phase 95%. Okay, so I got it right. Okay. So the question asks for let's the enthalpy and the percent weight. What is the percent weight? What is the composition? You only know, is this composition? No, this is not composition, is it? 0.95%. 95% of it is liquid phase. Okay. You cannot say that's composition, isn't it? Because both of them are ammonia. This is ammonia. This is also ammonia. Both of it is ammonia. Okay. 95% is liquid. 0.05 is also ammonia. 95% is also ammonia. It's not composition. It's just different phase. One of it is liquid, the other one is vapor. So you need to find the composition. X is what, and what is the enthalpy of your mixture. Okay. So now, is there any mention of the temperature is 160? So we're going to find 160. This is 160. That is 160. I'm trying to get it right on the, not successful with that. Okay, 160. That is 160. So the composition of your liquid, can get it from that line, not a straight line. I'm going to delete that. Okay, that is about 0.08 roughly. So if you go through, it's just roughly a rough estimate of 0.08. So that is for your liquid, and the enthalpy, if you read through the enthalpy, that will be 110 maybe. So enthalpy is 110. Your composition for the liquid, this is for the liquid phase. That is for your liquid phase. So this is your liquid, but this is liquid. So that will be 110, the enthalpy of your liquid. So liquid, let me write that here. Liquid, the enthalpy, specific enthalpy of liquid, 110. 110, the unit is BTU per pound mass. And now for your vapor, you do the same thing, except that you'll be going to the top of this curve. So you'll be going down vertically. Ouch. Let me undo that. To get the composition of your vapor. Your vapor, the composition of your vapor is, I did not write down the composition of the liquid just now. Composition of the liquid just now is about 0.08. Okay, that's liquid. The vapor, composition of your vapor. Let's use, oh dear, wait, okay. XV equals to about 0.66 maybe, or 65. It's not 65, it's about 66 roughly. Okay, that's pound mass per pound mass. Okay, this is pound mass per pound mass. And the enthalpy for your vapor, enthalpy of your vapor, you can read it by going horizontally to the y-axis. That's about 830 roughly. Okay, so that's 830 BTU per pound mass. Okay, so if we want to find the enthalpy of the mixture that we have, if we want to find the enthalpy of that mixture that we have, so we just do it using our value that we obtained here. Okay, hold on. The amount that 95% is liquid. So using that statement, 95% is liquid, and the other 0.5% is vapor. So you're going to multiply it with your enthalpy. So 0.95, I should be using a black ink. 0.95 pound mass of liquid. I don't need to write the whole thing liquid. I just write 0.5 times by the enthalpy of the liquid, which is, give it that value, plus the amount of the vapor, pound mass, times by the amount of your vapor. You should come out with your final enthalpy of your mixture per unit pound, because you assume 1 pound earlier. So your final enthalpy will be per unit pound. Even though if you cancel it, this is per unit pound. Let's do the calculation. At 0.95, if you write down the unit per HL over here is 110 BTU per pound. If you cancel the pound, you are left with BTU, but you already assume 1 pound of your mixture, so your answer will be BTU per pound. Let me erase this or else you get confused. And so plus 0.05 times by the enthalpy of your vapor. So you will get a final answer of, it will be different from the textbook because of the different values that we get for the enthalpy. That's equals to 146 BTU per pound. Even though you already cancel out the pound, but we know this is your unit per unit pound because of the assumption that we did earlier per pound of mixture. So this is your final answer, 146. The answer from the textbook, 147. We managed to get 146. That's very close. And let's see, the 8% of the liquid composition, we got 8%. the 64% of the vapor, we got 66. So that's a bit off, but not, it's still correct because we are getting that value from the graph. It's not a direct calculated value, so that's fine. So that's how you get the enthalpy of your mixture when you have liquid and vapor in equilibrium. Don't worry too much about this because you only come across this in separation. There's no energy balance here. This is just trying to get the enthalpy of your mixture that is in equilibrium, the liquid and the vapor in equilibrium. And this is how you get your enthalpy. Any questions? Are you guys with me? Or are you sleepy?
Yes, doctor.
Yeah, good. Thank you very much. You're still alert. Yeah, I should do something that involve you guys, but unfortunately, when you're doing online, well, it seems to be I'm the only one doing the talking here. So this is one example from your textbook. Any question, guys? Any questions? You guys tired? You need to do your preparation for test 3, and you need also to complete your mini project. Mini project is really not really mini, isn't it? There's a lot of work to be done. About the mini project, before I proceed to the next example, just give you guys some time to before we jump into the other example. About a mini project, since you're doing it in a group, there will be a peer rating. You know, everybody will rate your colleague, not your colleague, your partner in the group. How you grade is done online. I think they're going to set up a Google form. You're going to evaluate everybody in your group, and you will be also be evaluated by your members. So that is going to be, you know, you're going to be given a certain percent for that peer rating. I don't know how many percent it's going to be, but well, if it's a lot and you are not doing much, and if you are being graded poorly, oh my God, that is not help. That's not going to help you much. Okay, so that's about your mini project. Dr. Jamaros Liza is going to upload the Google form, and she will inform you guys. And she will give the other section the link, so everybody should be able to create your group members. Okay, so there are a few complaints about the sleeping partners, the group sleeping partners. So that's unfortunate. If you are not contributing to the group, then I don't think you're definitely not going to get a high rating from the other members. Okay, guys, so it's almost 3 o'clock. Take 5, please, and be back by 3:01. Sorry, 5, yeah, 3 o'clock. Be back by 3 o'clock. I will share the QR code so that somebody that just joined us can scan through. Okay, take a break. We will look at another example after this. Hey guys, I hope you have refreshed yourself. Okay, welcome back. I need to, before I leave this example at 5.4, let's just look through the problem just now. You have 1 pound of ammonia solution. This is the previous example that we just did. You have 1 pound of ammonia solution. 95% of it is liquid. It is liquid 95%, and you have 5% vapor. The composition of this let's use red. Okay, composition of that mixture is unknown. If the question asks for what is the composition of your mixture, you cannot just get 0.95 divided by 1 and then 0.05 divided by 1. That is not composition, because that is liquid but not the composition of your mixture. That is your liquid and your vapor, but not the composition of your mixture. Your composition of the mixture should be gram per gram of ammonia, and the rest are 1 minus X equals to gram per gram of water. So that should be the case of composition. Because this is liquid, that is vapor. It's not composition. So you need to get it right. So in order to get the composition, all you have to do is, based on the value that you just got just now, this is for the liquid, this is for the vapor, you should be able to get the composition of your mixture. So if you do the same thing as what we just did just now for the enthalpy, but this time you'll be doing it for composition, so all you have to do is, this is for liquid, the amount of liquid in your mixture. So time by the amount or the composition of your liquid, 0.08, and the amount of vapor, time by the composition of each vapor. So you should be able to get, if you do this, you should be able to get the composition of about 0.109. That's the composition of X of your mixture here. That is your X. But if you want to do it using the graph without calculating it, you can do so, because remember, you know that you have the enthalpy of the mixture. This is the enthalpy 146. So if you locate that enthalpy, it would be somewhere here. If you look at the enthalpy, it would be somewhere there. So if I'm going to use a different color, let's use green. 146. Make myself a straight line. Okay, that's about it. Hope that's a straight line. It's not really a straight line, it's slanting. Let me try to get a straight line. Okay, that's 146. Is it 146? Maybe it's not 146. Maybe I just move it a bit up. That's too high. Okay, 146 maybe. Okay, so I extend it. Okay, until you intersect the 160 Fahrenheit, because your solution is at 160 degrees Fahrenheit. So where it intersect is going to be your composition. Oops. Okay. The composition is going to be touching the 160 with the horizontal line. So if you go downwards, that will be your composition. So you can estimate it's sort of 0.1, this is 0.15, this is about 0.13, which is a bit off from our calculation. Our calculation, we managed to get approximately 0.11. The value that you get from the graph is 0.13, but if you calculate it, it's going to be about 0.11. Obviously, if you're using the graph, it will be a bit off because of the errors in estimating the enthalpy of 146 earlier. And then at the point of intersection, it might be a bit off. So there's a slight difference from the calculated value and the value obtained using the graph. But that's how you should be able to get the composition of your mixture. A mixture of ammonia and water, having liquid and vapor in equilibrium. Okay. So any question on that, guys? Any question on that? No? Okay. So let's go and look at example 855. We have done 83, 84. Sorry, 853, 854. Now we'll be looking at 853. Sorry, 4. No, 5. Keep on getting is 855. Okay, now I don't need this actually, and I'm just going to erase it. In this question, let's read through the statement. You have 30% ammonia solution at 100 psi A. You're going to fit it into a tank. This tank is actually just not a simple tank, it is a flush tank. A flush tank means you're going to vaporize part of your liquid. The initial feed is a solution, is liquid. So when you put it in a flush tank, there's a drop in pressure. Okay, the pressure here is given 1 atm. Okay, I wonder what is 100 psi in terms of atm. Should be higher than 1 atm. Okay, it should be higher than 1 atm because when you put a liquid into a flush tank, the pressure of the flush tank should be lower, and when it encounters the certain drop in temperature, the certain drop in pressure will cause the liquid to vaporize, part of it to vaporize. So you will have two output stream. One of it is still in a liquid phase, the other one is in a vapor phase, and the liquid and the vapor will be in equilibrium. Okay, so the enthalpy of your feed relative to figure 852 is given 100 pound mass per pound. Sorry, not mass, BTU per pound mass. That is the amount of the enthalpy of your feed. The vapor composition of your product is 89%. Weight, mass percent. Determine the temperature of the stream temperature output, the mass fraction in the liquid, the flow rate of the liquid and the vapor coming out, and the rate at which heat must be transferred to the tank or vaporizer. So you have to get the correct picture of what is going on here. You have a liquid coming into a flush tank. When there is a drop in pressure, your liquid will vaporize. So you have two streams. Part of your liquid will vaporize, not completely vaporize the whole thing, no. Part of it. So one stream will be in a vapor phase, the other stream will be in a liquid phase. So we draw the diagram. Try to squeeze everything here. Oh, that is not what I want. I need to delete this first. Okay. Let use a black color. Now I have my input, my liquid. Yeah, and I have my output. Let's undo that. My output. Oh God, not doing a good job there. Yeah, that's the vapor, and this is going to be your liquid. So coming in, you have 0.3. You're going to use pound mass per pound mass of ammonia. The rest will be water. Coming in at 100 psi. And what is the temperature coming in? At a rate of 100 pound mass per hour. There's no mention of temperature to a tank, where the pressure here is 1 atm. Okay, here is 100 psi. Make sure whenever you have your you draw your block diagram, you need to label everything. You need to make sure that every information is listed down in your block diagram. So the enthalpy of the feed is given 100 BTU per mass. That is the enthalpy of the feed. So let's give it subscript 1. Okay. The vapor composition, this is your vapor. This will be MV pound mass per hour of vapor. Right, that's your vapor. I don't have enough space to write vapor, so it's obviously you need to write vapor, but I don't have enough space to write. The composition of your vapor is 0.89 pound mass per pound mass of ammonia. and the rest will be that of water, 0.11 pound mass per pound mass of water. Okay, so this bottom stream coming out will be that of your liquid stream, pound mass per hour of liquid. You need to write down liquid there, but I don't have enough space. And the composition you don't know. Pound mass of ammonia, 1 minus X pound mass per pound mass of water. Okay. That's the diagram. Anything that I need to add to that diagram? Okay, that's more or less it. Okay. Your basis, every time you have material balance, you have your block diagram, you need to have a basis, your 100 pound mass per hour of feed or fat. 100 pound mass being fat or feed. It's just you can put feed or you can put fat, no problem. It's just a matter of English. Okay, now in order to find the flow rate, let's see whether we can do the total balance, the material balance. Material balance for the total balance, 100 coming in, coming out will be the mass flow rate of the vapor plus the mass flow rate of your liquid. So you have two unknowns. Guys, whenever you have a problem, you need to do your degree of freedom. I'm not doing the degree of freedom. You need to do your degree of freedom to check whether you can solve it or there's not enough information for you to solve it. So let's do the ammonia balance. Okay, so coming in, you have 30% ammonia, so 0.3 times by 100, that will be the amount of ammonia coming in. The amount of vapor, the composition of the vapor is given 0.89 times by the mass flow rate of the vapor, but the amount of your composition for the bottom, liquid bottom, the composition is unknown, and also the flow rate of that liquid flow rate is unknown. So here you have your second equation, but unfortunately you have 1, 2, 3, 3 unknowns. Okay, from the second equation, you have your X there that you need to solve for beside the mass flow rate. So that will be 3 unknowns. You only have 2 equations. Definitely you cannot solve it using both equations. There's no way of solving it. So you are left with the diagram in order to solve for your unknown. So let's look at this diagram. You are given the enthalpy of your feed, which is 100. So your enthalpy is here, 100. Okay, that is your enthalpy, 100 BTU per pound mass. And the composition is 30% ammonia or 0.3. So this is 0.3. Okay, so the point of intersection is here. That is your feed. Now, what are we going to do? We need to find the composition X. Your X is your liquid. Your X is your liquid. If you look at the point here, it's not really exactly on the line, the isotope, the tie line. So let's just draw a straight line through the tie line. You don't really get it directly on the tie line. So draw a tri line per more or less midway between that. Okay, try to get it. Okay, so this is going to be the composition of the liquid. Okay, that's the liquid. And here the composition of the vapor is not really 0.89. Here is given 0.89. Here we get more than 0.89, but 0.9 something. So let's look at the answer. The temperature is 120. How come I got 110? The temperature given for the solution here is 120. When I did this, because this is 100 BTU, So I look at 100, that is 100. Okay. And my composition for my feed is 0.3. So that is my feed. That is my feed. Why am I not getting 120? Somebody, can you please respond? What is being asked? What is being asked? The question asked for the temperature of what? The temperature of the stream leaving the tank. Okay, the temperature of the stream leaving the tank, not the temperature of the feed. This is the temperature of the feed. Okay, guys, that is the enthalpy of the feed. So that's why it's wrong. So I need to get the temperature of the output, not the temperature of the feed. So now let's go to our composition of the output. The output composition that we know, we have 0.89. Okay, 0.89. So we're not going to look at that composition of the enthalpy just now because that is for your feed. We're going to look at the output because the question asks for the output temperature. So look at the composition of your vapor. 0.89 is roughly somewhere here, somewhere close to 0.9. Get a straight line. Try to get a straight line. Is it 0.9? It should be, well, that's about 0.88. So let's get it close to 0.9. Okay, that is as close as I can get. Actually, I need to extend it further. Somewhere there, huh? So that will be the temperature if you zoom it up, isn't it? If you zoom it up, it's not really on that. It's not really. Let me use a different color so that you can see. It's not really on this line, isn't it? It's not 120. It's just slightly above 120. It's slightly above 120. But if you want to, you want to say that this is 0.89. Oh, I'm not going to do a good job here. It's too large. 0.89. Your product. Okay. So that is about close to 0.9. And if you look here, if we zoom in, it should be somewhere here. That is the temperature. Your temperature will be quite close to 120, quite close to 120, but not really on that 120 degrees Fahrenheit. So if you want to say it's 121, well, this is let's see, this is 140, this is 120. So you can say maybe 122, maybe it's up to you. But the answer in the solution is 120. Because if you look, it's almost 120. Okay, so I would give it 122. I would say the temperature would be, the output temperature is 122 degrees Fahrenheit. I would just give it an estimate of that temperature. It's not really on that 120 line. Just now we got it wrong. This is not the output. This is the feed. The enthalpy of the feed is 100 and the composition of the feed is 30. So that is the feed. The question asks for the temperature of the stream leaving the tank. So it should be the output stream. Okay, now once you know that temperature, that's one of it, but still cannot solve the material balance. You don't know this X. What is this X? You don't know. So now, since you already know that it should be somewhere along this same line, 122 line. Let me try to get a straight line. Okay. So when you projected it to the liquid line, you should be able to get the composition of your liquid. Okay, so that is the composition of your liquid. In this case, we gave it a symbol of X. So that is your X. That's about 0.18 roughly. That's 0.5 is here. That's about 0.18. So if I use like in. So that becomes 0.18. X equals to 0.18. So now you are left with only two unknowns. From the first and the second equation, the first two equation for the first and the second equations, you can get your flow rate. So now from the first equation, you should get mv equals to 100 minus ml. Substitute it inside this equation. So it will be 0.3 times by 100 plus 0.89, 100 minus ml, plus 0.18 is the composition that you got just now from your graph, and that's ml. So the only unknown is ml, so that's 30 plus 89 minus 0.89 ml. Oh, what am I doing? There's no equal sign here. There's supposed to be an equal sign there. Right? There's supposed to be an equal sign. Yeah, plus 0.18 ml. So if we rearrange ml on one side, 0.89 on the left side minus 0.18, you have 89 minus 30. So your ml is equals to, what's the unit we're going to use? Pound per hour, pound mass per hour. So if you do the calculation, 89 minus 30 divided by the difference of 0.89 minus 0.18, you get your answer 83.1. So what's the answer? Is there a flow rate? 83. I got 83.1. The answer given is 84. The composition just now is because of the different in composition. This one is 0.85. We got 0.8. So that's why our flow rate is different. When we look at the graph, we got 0.18 because it's not really on the 120 degrees Fahrenheit. We are slightly above. We got a temperature of roughly 122. The composition obtained by the author is 0.185. We got 0.18. That's close. The flow rate of this is the flow rate of the liquid. The author got 84. We got 83.1. That's close. So now solve for the flow rate of your vapor from the first equation, mv equals to 100 minus 83.1. So if you do that calculation, that will be 16.9 pound mass per hour. So that is the flow rate of your vapor. So we got 16.9. Obviously, it's not going to be the same as the solution because we already got lots and lots of different values before this. So it's definitely not going to be the same. So next, the question asks for the amount of heat that need to be transferred to the vaporizer. So what is Q? So what is Q? With a dot there. So now you have your feed, the enthalpy of your feed, you already have it. You need to get the enthalpy of both the vapor. Give this enthalpy 2 and enthalpy 3. Q, if you do the energy balance, the equation, delta H, this is an open system. Again, drop terms that is not, that can be dropped. Give reasons. You end up with Q equals to delta H. And that is always out the amount of molar flow rate times by its enthalpy minus in the product of the molar flow rate with the enthalpies. So now let's see. We have the first enthalpy. We have the mass flow rate. We have the mass flow rate for the feed. We already have the mass flow rate for the vapor and the liquid, but we need to find the enthalpy of the vapor. The enthalpy of the vapor we denoted as, oh dear, what did I do? We denoted it as H2. Okay, so we need to find that H2. So we know that the vapor is on the saturated vapor line. So we're going to project this horizontally. So that is roughly the enthalpy of your vapor. H2 is about 700 and let's see, this is 50. That's about 720, maybe 730 roughly. It's a rough estimate. Right. So that's about 730. So H2 is 730. The unit is BTU per pound. I don't have enough space there. So we're going to do the same thing for H3, which is for the liquid. If you continue along the 122 line, you come across the liquid on the saturated liquid line, so projected that horizontally. So if you look at that, the scale, I would say that's about 50 is somewhere here. Okay, so that's about 40, just a rough estimate. So that is going to be 40 BTU per pound. That's all. I have everything there. So all I have to do now is get my fill it up in solve this equation. The output, there's the mass flow rate of V, MV. What is our MV? Our MV is 16.9. That's the flow rate of your vapor. The enthalpy of your vapor just now we got 730. Okay. Plus the flow rate of your liquid. We calculated ml 83.1. And you do this, you multiply it with the enthalpy, which is we estimate to be 40. Could be 35, could be 40. It depends on how you look at the graph. And minus the input, sorry, the stream coming in is the same thing as input. 100 is the flow rate, time by is enthalpy of 100, the same 100 time by 100. Yeah. So if you do the calculation, your answer will be, let's see, your enthalpy is BTU per pound, your flow rate is BTU pound mass per hour, so this will be BTU per hour. So let's do the calculation. Okay, I get a value of 5661. That's my amount of heat that need to be supplied in order for the process, in order for the stream, which is in liquid form, to vaporize. So let's see the answer. Okay, the answer here, 5400 BTU per hour. I got 5661. That's a bit different, big different because of the values of my enthalpies that I managed to get. Let's see the textbook, the enthalpy from the textbook. Okay, the textbook, the author, let's put this in red. The author for the enthalpy of the vapor, the author got 728. There's a difference there. And for the enthalpy of the liquid, the author got 45. Yeah, so definitely the accumulated difference is from the enthalpies, but the enthalpy of the feed is already given, so it's not going to change. So obviously it's going to be different also due to the flow rate that we calculated earlier. The flow rate earlier was different from the author. The author got 84 and 16. We got 83 and 16.9. So the errors, not really error, the differences accumulated due to the differences in the flow rate and the enthalpies. So this is your final answer. Yeah. So this is how you do the calculation using the enthalpy concentration diagram. You don't make the mistake like I did just now. I got the point for the feed. I thought that was the question was asking for the temperature of the feed, but actually the question was asking for the output temperature. So that's why I made a mistake just now. If I want to know the output, the temperature of the inlet, I can do it using the point, this point, which is the feed. Hey guys, any questions? Any questions? This is mixed. This is not really mixing. This is vaporizing. This is not mixing. This has nothing to do with table B11 at all. Okay, and then every time you do your energy balance, please write down I forgot to write down the reference state. Every time you have enthalpy, you must have a reference state. So reference state must be the same as that of the graph, which we got the enthalpy from. So we got the enthalpy from this graph. So our reference state must be the same. Liquid water at 32 degrees Fahrenheit. 32 degrees Fahrenheit. I'm assuming it is at 1 atm. And we have ammonia. What is the state of ammonia? Is liquid ammonia at minus 40. Okay, liquid ammonia at minus 40. Okay, so that is your reference state. So every time you do matter energy balance, you must have your reference state. Every time you do your mass balance, you must have a basis. So get into the habit of putting these two basis and reference state. And another one more thing that you need to get into a habit is of doing the degree of freedom. Because if for this case, you know that you don't have enough information, there's no way you're going to be able to solve it. But do your degree of freedom. Whether you can solve it or you can't, it depends on your degree of freedom. If it's 0, then you can solve it. Okay, so get into the habit of doing the degree of freedom too. Any question, guys? Any questions? Everybody, are you still with me, or are you too tired? Somebody? Not enough? What do you mean, Ibrahim? Not enough what?
This was about material balance.
Material balance. Okay, not enough information. Thank you. Okay, yeah, not enough information. You can't solve it. So anybody, any questions? Anything you need to, you want clarified? Okay. This is yes.
How would I find the
what?
condensation of a mixture?
Can't catch you there. The what mixture?
The T bubble or T condensation.
The dew point and the bubble point. This will be, you'll have your vapor. Your vapor will be at a temperature of, okay guys, in this case, you already know what is the output temperature, right? The output temperature is 122.
This is a side question.
Because the liquid and the vapor, they are in equilibrium. But if you want to get the dew point and the bubble point, then you look at the composition. You look at the composition and you do the calculation for the dew point and the bubble point, because that will be different from what we're doing here.
Okay.
Okay, because this is they are in equilibrium, but the temperature is the same. The temperature is the same for the vapor and the liquid because they are in equilibrium. Thank you, Ibrahim, for that. You can look it up. There's a lot of example on how to get the dew point and the bubble point. The dew point will be for the vapor. The bubble point will be for the liquid.
All right.
Okay. Any other questions? No? No questions? Wow. Everybody very quiet. Normally, when I'm conducting my lecture online, there's a lot of question on when I'm not online, face to face. But normally, when I have the lecture done face to face, there will be lots and lots and lots of questions. Somehow, when it's online, the number of questions seems to decrease. I don't know whether you understand or you don't understand at all. So I have no idea. Okay, since there's no questions, I'm not going to start a new topic. We're going to go into energy balance of solution that is going to be in in chapter 9. This involves reaction. Okay. Okay. What I'm going to do for the rest of the time, I have not this. Where is my other notes? The energy balance, not for. I need the reactive one. I need to. For the rest of the time, I want to show you guys. Not this one. Energy balance of solution. The reactive. Oh, this is the number. Hold on, guys. I need to find my notes. Okay. You are going to come. You need to review the multiple reaction. Okay. So I have over here. I'm not sure whether any of you have done it. Alright. So you need to know this part, yield and selectivity. You will have, whenever you have multiple reaction, you have 1 or 2 or 3 reaction. So you have one equation, for example, the desired product. That is your desired product. For the second reaction, undesired product, the side reaction, the one that you really doesn't want to have actually, you wish it doesn't exist, but unfortunately, you always end up with what you want and you end up with what you don't want. Okay, so you have two equations, for example, your desired product and your undesired product. So for selectivity, if you look at the definition of selectivity, this is your amount of desired product, this is the amount of your undesired product. So that is selectivity. So the amount of your desired product that is formed divided by the amount of your undesired product being formed. So I'm doing a revision here. And if you're talking about yield, the amount of your desired product, okay, divided by the amount of the desired product if there is no side reaction, there is no second reaction, there's no third reaction. And if the limiting equation, the limiting reactant completely consumed, that means there's no output of your limiting reactant. It is completely consumed. So that is the definition of yield. You have the mole of the desired product being formed divided by the mole of the desired product. But in this case, it's as if there is no side reaction at all, and the amount of the limiting reactant is completely consumed. Okay, so that's the definition that you need to know. You might be given one of these, one of it, not both. It could be yield, it could be selectivity, and the other one would be your fractional conversion. Sorry, I always do this. The fractional conversion. The fractional conversion is normally also given for your limiting reactant, maybe. Yeah, if you have more than one reactant, then it definitely is going to be your limiting reactant. So that amount should be also be given. Okay, so now let's have a look at this. I'm doing the revision now for you guys. Okay, this is from chapter 4. This is from chapter 4. This is metal balance. It has nothing to do with energy balance. But from your metal balance, you can proceed to your energy balance. Okay, now you have reaction 1, reaction 2. This reaction involves ethane. So your ethane, this is your ethane. Going to be, you're going to form acetylene. This is acetylene. That is acetylene. Okay. But unfortunately, from the second reaction, you're going to form methane. Okay. From the first reaction, you get is ethylene. But from the second reaction, you're going to get methane. So I have the block diagram here. The composition of your feed is 85% ethane. So that's 85% listed here. The inert, there's an inert. We don't know what inert it is. It's just specified as inert. So the rest of the composition will be for inert, 0.15 mole of inert. And the fractional conversion of ethane, the fractional conversion is equal to 0.501. You have ethane, the amount of ethane you don't know. You can use that basis, maybe 100 mole. Let's see, what did I use over here? I use 100, is it? Okay, I use 100. So my basis, I said basis 100 mole of ethane. So my ethane fat. So that's going to be 100. Oh dear, I forgot the mole. Yeah, that's mole. Could be mole per hour, could mole per second, is up to you. Yeah, so that is going to be, if you look at the equation, there's two equations. So if you draw the table, yeah, I'm going to just do it roughly. After that, we're going to scroll up. Is your E10, C2 is 6. That, oh, wrong. That's not E10. That's going to be input. Put the number of mole. This is the amount that is going to react or being consumed, going to be generated. This is your output. I'm using the extent of reaction method here. Yeah, I'm using the extent of reaction method. So I'm going to have E10 as one of the components. I'm going to have ethylene being formed. I'm going to have hydrogen being formed. Yeah, I'm going to have methane being formed. This is using extent of reaction method. Oh, not a good line. Okay. So you know your okay, because there's two equation here. I need one more row. I forgot about that. I need one more row. This is for a single reaction, so I need to have another row. This is the first reaction. Got another row for the second reaction, and this is my output. I'm overlapping here. You will not be able to see. Can you? Okay, I think you can see. But this is for the second reaction. This is first reaction. That is second reaction. This is output. Sorry guys, I should have put it higher up. Yeah, let me undo that. Else it's overlapping. I'm doing a revision here. Most probably you guys already looked at this example. For those who already look at this example, you can just exit the meeting. It's okay. Input, put the number of mole. I'm not going to put that. Plus or minus. Again, I don't have enough space. I want to do it because the solution is there, but I thought better do it so that you can see what I'm doing. Okay. This is going to be the output. This is going to be the second reaction. It's going to be the first reaction. It's going to be your input. And lastly, this is for the chemicals. Okay, so this is going to be your ethane. You're going to have ethylene. You're going to have hydrogen. You're going to have ethane. Okay, well, there are lots of space there. I can actually put mole here, mole there, and mole here, and mole here. I don't have enough space. Okay, what is the amount of ethane coming in? 100. From the first equation, you have one stoichiometric coefficient for ethane, so that's -1. The bracket is for your extent of reaction 1. For the second reaction, you have also 1, the coefficient for ethane, -1. Both ethane is on the left-hand side of the equation. That means it's being consumed. So that's why there's the negative there. And this is your final value for your ethane. So over here, I have listed the symbol for ethane. Why? I think I got mistake here. It's supposed to be 2 here. Okay. So that's N1. N1 is the amount of ethane in the output. So I'm not going to write that there. And now, I have, from the first equation, I have ethylene being formed. Again, the stoichiometric coefficient, sorry. I got to put it. Okay, that's 1. So that's going to be +1 from the first equation. There's no ethylene being formed in the second equation, so put a dash there. There's no input of ethylene, so put that dash there. Okay, so you don't know what is the output. And next, for hydrogen, hydrogen is going to be consumed in the second equation, but there is no hydrogen in the reactant, but there is hydrogen in your product. So let me undo that. I better just highlight it using highlight. That is your product, that is your reactant. Okay, so for hydrogen in the first reaction, it is being produced, so plus. The stoichiometric coefficient is 1. This one here. Okay. For the second reaction, this also 1. But it is being consumed, so you must minus. Minus 1, that's plus 1. Okay. So there's no hydrogen in your feed. You only have ethane in your feed. So for the second reaction, you have methane. You don't have methane in the first reaction, so that's minus. There's no feed. There's nothing in the first reaction. But in the second reaction, you have methane here, and the stoichiometric coefficient is 2, so you're going to put 2 plus 2, and the extent of reaction for number 2. So now, what information is given? You have the fractional yield. You have the conversion is given, and you have another thing is yield. Yield of ethylene. Yield of ethylene. That's the yield of ethylene, 0.471. So that's going to be ethylene is going to be formed. Definition of yield just now, mole of your desired product divided by mole of desired product if there is no side reaction and all of your reactant being consumed. So that means if there is no desired product, that means this is the only this is the only reaction that is going to occur if you're looking at yield. So this is your only reaction. There's no side reaction based on the definition of yield. So if you have 100 mole here and all of 100 mole is going to be consumed, you're going to form how many ethylene? How much of ethylene will be formed?
100.
100. Okay, that's going to be 100. That is ethylene. So the yield is ethylene, the form, the actual being formed, but the amount of ethylene that is formed without any side reaction. Without any side reaction. Without any side reaction and complete consumption of ethane. Yeah. So if you do that, your amount of ethylene that is being formed, let's see, if I use that symbol here, my ethylene being formed is, where is ethylene? This, N2. So if I use that symbol, N2 divide by 100. The 100 just now is the one if 100% of ethane is completely consumed and you have no other side reaction. This is the only reaction that is occurring. Then you have 100 ethylene being formed, so that will be ethylene. So that's going to be 100, and that yield is given. Let me erase this because I need space. That amount of yield is given 0.471 from the statement of the problem. So that means from here you should be able to get N2. N2 is equal to 47.1. Okay, so N2 is for ethylene. And if you look for ethylene, this is ethylene, that is 47.1. So now you should know what is this extent of reaction 1. Because there's no other, if you look at this, just at this column, just at that column, you only have one unknown. That unknown is the extent of reaction. Extent of reaction 1 is equal to 47.1. So based on that column, you should come up with your extent of reaction 41. So from there, I erase this. I don't need to erase. Just proceed. That is going to be 47.1 for all the extent of reaction 1. Okay? So now you need to find the second extent of reaction. So what else do you have? You have the fractional conversion 0.501. So let's highlight this fractional conversion of ethane 0.501. Okay? So fractional conversion is equals to, what's the definition of fractional conversion? If you don't remember the formula, look at this column. Now I'm going to use a different mark color. Okay? Look at this column. This is for ethane. Look at this column. Okay? Your 100, this is your your fractional conversion should be, how do you know, do you remember what's the fractional conversion formula? Anybody?
React over fit or in minus out
In minus out.
over in
Okay, minus out over.
divided by in.
Okay, so the amount in just now is 100 minus n out, you don't know, divided by 100. And that value is given 0.501. Yeah, that's using formula. If you don't use formula, you can look at this symbol over here. Okay, so you know this is n, and you look at this column, I'm sorry, n out, so that's n out. So if you look at this, you can find extent of reaction 2, isn't it? Can you? If you use
Yes.
that, okay, so 0.501 is equals to 100 minus n out divided by 100. So n out, if you do use this formula, the formula that you gave me just now, is equals to that's about 100 minus 50.1, is it? Rearrange it. Is that
Yeah.
correct?
Yes, yes. It is
Okay.
49.9 and out equal to 49.9.
49.9. Okay, thank you. That's more. So that is n out. So if you put that value 49.9 over here, okay, put that value 49.9 over here, you should be able to come up with what is your external reaction 2. External reaction 2 is going to 100 minus 47.1, and then what? Minus extent, sorry, I got it. Let me undo that. Okay, let me put the output here, 49.9, okay, is equals to 100 minus 47 minus external reaction 2, right? Is that right? Look at this column. Yeah, 100 minus 47.1 minus external reaction 2 is equals to 49.9. So you will get your external reaction 2. So if you do the calculation, your external reaction 2 should be, if you do it, 2.585. Should be 2.585. Should be. Because over here I have the answer. Did I got wrong? 40. External reaction 1 is 40. What do we got? External reaction 1? 47. How come I got it wrong? It's not the same as the solution, guys. Did I make a mistake somewhere? The answer here is different. Yeah? Oh, guys, I know why I make mistake. Do you know why? Somebody point out to me.
The inlet is mixture. You put it 100 as
Yes. That's my mistake. I put this total flow rate. It should be only for E10. So that's why my mistake is. Okay? I should put 85 here. This one should be 85. Okay? Then I can get my actual answer. So it should be 85 here. This one become 85. This one become 85. Okay? That's my mistake. Okay? Because it's a composition, there is a mixture, just like what he said. So this one will be different. This one will be different. Because where did I get it just now? That is 85. That is 85. That is also 85. Okay? So this is going to be, you calculate it, that is going to be N2 is equals to 85 times by 0.471. Okay? So that's, will give you the same answer as the solution. Yeah, 40. Same as the solution. That is your extent of reaction for number for this one. This is should be 40. Yeah, so that is extent of reaction 1. That is the extent of reaction 1. So that is the same as here, 40. I make a mistake, guys, because I put that value as for E10. It should be only here is for E10, 85 mole. Because I need to multiply it with the total flow rate. It's a mixture. Okay, so that's my mistake. So now this should be 85, this should be 85. That's where I need to correct my calculation. Anyway, the time is almost 5 minutes to. Let's see whether we can get the correct answer for N out. 85 times by 0.501. Okay, my 85 minus the answer, I should come to 42. So my N out, this one 85, this one 85. My N out is going to be 85. Okay, this is going to be, this now I forgot already, but I will come up with 42.415. Okay, I forgot already. 85 times by, this one should be 85 times 0.501. Yeah, so that's the answer. So this is the N out 42.415. So this one should be 42.415. So from there, you should be able to calculate your extent of reaction 2. Once you manage to get the extent of reaction 2, put the same value over here and over there, you are done with your meter balance. So let's do our extent of reaction 2. That's the wrong answer just now. This should be 42.415. Let me equals to 85. I'm looking at this column highlighted in red, minus this one just now is 40. That is 40. That is 40. We just calculate. We just make the correction just now. That is equals to 40 because we make a mistake just now. So minus 40 minus acceleration 2. Okay, I'm just looking at this column highlighted in red. 85 minus 40 minus extent of reaction 2 equals to 42.415. So extent of reaction 2 is equals to, if we do the sum, come up with 2.585. That is the answer given here. Okay. Initially, when I put that value, where did I put it? Okay, here. I did not get it correct. This one is the answer that I got from the solution. But this is the extent of reaction 2.585. So if you put here 2.585, 2.585, that will be 2 times by 2. You multiply it by 2, you will get 5.17. And over here, 40 minus 2.585 will come up with 37.415. I forgot my inert. I have to put my inert because I forgot there is a mixture. My inert is, in the question, my inert is 15%. Of the composition. The composition is 15. So this is going to be 15. But it's not going to be involved in the reaction, so that's going to be 15. So that is the final value. It's a bit messy, but in the short space of time, this is what I managed to explain to you guys. You will end up with the same answer as, where is the answer? Okay, there's the answer. Yeah, that's the answer. I got 5.17. I got 5.17. Here is 5.2, it's rounded off. For my hydrogen, 37.4. I got 37.415. For ethylene, I got, should be same, 40, same 40. So that solves your problem. So remember, this is how you deal with multiple reaction. You might be given yield, you might be given selectivity. One of it will be given selectivity. Selectivity. I got it wrong, the spelling. I'm in a hurry. Okay, selectivity there. In a hurry. So, okay, that's selectivity. And one of it is fractional conversion. So one of them, two of them will be given. Might be this, or might be that with that. Two of them will be given, not all three. Okay, so when you have multiple reaction, so this is how you solve multiple reaction using extent of reaction. You need to draw the table, construct the table so that you can see what's going on, and don't make a mistake like what I did just now. I put that value inside here, which is wrong. It's a mixture. Okay, thank you guys. It's already 3:59. So thank you very much for your attendance, and please do more revision on the reaction for multiple phase for the energy balance. This is just the meter balance. So do more revision on the energy balance that involve multiple reaction and also single reaction. Okay guys, Assalamualaikum warahmatullahi wabarakatuh. My God, nobody going to rescue.
Thank you, Doctor.
You're welcome.
Thank you.
You're welcome.